So first we'll go with recap, what we discussed, then we'll move into logistic regression. We started with linear regression. See, when we talk about linear regression, okay, so we started with hypothesis function. Okay, so we discussed about what linear regression is. Okay, so regression is a continuous problem. Okay, if the target is continuous, then means continuous in the sense ranges from minus infinity to plus infinity. Okay, so that's basically a continuous problem. For that, we'll use linear regression. Okay, so the heart of linear regression is hypothesis function. So otherwise we can say universal function approximator. Okay, as I said, people use that particular term, universal function approximator, for neural networks, not for linear function, linear regression. But just for understanding purpose, you can use that. So when we discuss about neural networks, it would confuse a lot. Okay, so the formula for hypothesis function is y hat is equal to w transpose of x plus b. Where w and b are weights, or some people call coefficients. Okay, so given x, we have to identify w hat. Okay, but right now what we have both x as well as y. Okay, so what we need to do, that is the training data. So using the training data, we have to find a hypothesis function. The hypothesis function is w transpose x plus b. Okay, and then we have to find w and b. Okay, so and then how we can calculate what we find is correct or not. Okay, so let's assume that we come up with some w value and b value. Okay, and then how we understand this w and b are correct in order to predict the future thing. Okay, so for that we have a loss function. Okay, so assume that you have some let's open the Excel. Okay, assume that you have 5 training data. Okay, starts with x1, x2, and then y1, one output. Okay, so assume that you have 5 data. Okay, and then ranges from y1 to y5. So means you have 5 features and 5 targets. So what you'll do, you'll take all the 5 features, okay, y1, and then corresponding y hat for y1, and then for y2 corresponding y hat till ym, and still y5. Okay, and then you'll calculate the loss. Okay, so now how you'll basically approach it. Okay, so first of all, we'll initialize w and b to 0 value. Okay, so I'll initialize 0 value to w and 0 to b. Okay, I'll get some y hat. Okay, assume that my y hat is some value. Okay, basically equal to x. Okay, I know the y1 value. I'll substitute here y1 minus y hat, y2 minus y hat, ym minus y hat. I'll get some value here. That is my loss. Okay, so I calculate this loss. Okay, so what I need to do now, I understand my loss is high because this is the first time, this is the first iteration, right? So what I need to do, I need to calculate R square, because that will measure the accuracy. Okay, so my R square is 1 minus, okay, now you can think about it. Okay, so yesterday we discussed about average value, right? Okay, so if you go for an average value, you'll get something like this. Just go through this formula. Okay, so 1 minus y hat, otherwise you can read like this. Okay, y minus y hat whole square divided by y minus y average whole square. So this is the formula. Okay, so when you just unroll y hat, okay, y hat is nothing but w transpose of x whole square, and then y average is nothing but w transpose x average value. Okay, so that ranges from 0 to 1. Okay, assume that we initialize w and b, we calculate loss. Okay, so using that we calculate R2. Okay, R2 value ranges from 0 to 1. For the first time, definitely we'll get very less accuracy. So assume that our accuracy is 0.1 or something like that. Okay, so we have to increase to 1. Okay, so what we'll do, we'll increase the w and b value a little bit, and then we'll calculate loss and R square. Now we'll say R square is better. No, not better. Then we'll keep on do the same iteration until unless last and R square is good. Okay, that's what we're going to do. Okay, so now assume that we achieve some decent accuracy. Okay, so now how we can evaluate and increase the accuracy further, you know. So in this case I have in this case I have two features. Okay, so I need to think about it whether I can use all two features or I can use only one features which is very essential to this prediction. Okay, as I said, you may have number of experience and gender, okay, and salary. Okay, so male and female is not a problem. Okay, if they have a good experience, obviously they'll get good the salary. Okay, so we can remove this field. Okay, so in some cases we may have a business knowledge, using that we can remove, but most of the cases we don't have a business knowledge, we are not a business people. Okay, so what we can do, we can calculate p-value for each and every variable, means each and every futures. Okay, if the p-value is greater than 0.05, okay, then we can eliminate those features. Okay, so if you go to a statistics class, okay, so in statistics class we discussed about p-value. So if you have any question on the p-value formula, just revisit the statistics class. Okay, try to understand this. If you're not, okay, so if you have any question, you can come up with, you can ask me. Okay, and then we have some other techniques called multicollinearity. Okay, so p-value basically takes every individual value and then see the scores, right? But what multicollinearity will do, something like that. Okay, it sees the multicollinearity between x and x2. Okay, if x1 and x2 are both are multicollinear, then obviously we have to remove either one. Okay, that's what this multicollinearity will do. Okay, so how we can calculate multicollinearity? We'll have a formula called variance inflation factor. Okay, so the formula, right now I'm not going to discuss about the formula. Okay, so because this also we discussed in statistics class, variance inflation factor. Okay, if the variance inflation factor is greater than threshold, then we eliminate those features. Okay, that's what we discussed. Very simple. Okay, we talk about what is linear regression. Okay, what is loss function, what is hypothesis function, how we initialize W and B value. Okay, how we can assess the model, and then we'll keep on iterate. Okay, so once we get the good W and B, then we'll try to evaluate our model. Okay, so today we'll discuss one more thing, then we'll move into logistic regression. Okay, so now, so that we'll split the data into two. Okay, test data and then training data. Okay, so here I have 5 samples, right? So what I'll basically do, I'll use this data for training and I'll use this data for testing. Okay, so you can ask me why, because it's good if you split, because think about it, this is training data, and if I use all data for training, then what happens? I'll go for 5 iteration because I have 5 data. That's all. Okay, so assume that I'll take everything as a training data. Okay, so here I try to calculate R square as well as accuracy as well as loss. Okay, so let's not worry about R square. Okay, so from now on we'll talk about accuracy and loss. Okay, so we have accuracy and we have loss. Okay, so now if you take everything as a training data, okay, you'll get some accuracy, some 95%. Okay, in the real time you'll get some data. Okay, so now we created a model. Okay, and then so now you deploy the model into production. Okay, now in the real time you get some data, you hit the model. Okay, get the output. Okay, but one thing is missing here, because think about it, the data is coming from so many distribution, so we cannot say that the data is coming from only one distribution. Okay, what I mean by distributions, okay, think about it, you collected a population samples, okay, in India. So you collected some samples from Delhi, you collected some samples from Uttar Pradesh, you collected some samples from Karnataka, you collected some samples from Tamil Nadu. Okay, so obviously the density of the population, okay, is very different, uh, from every distribution. So Delhi is one of the distribution, Uttar Pradesh is one of the distribution, okay, Tamil Nadu is one of the distribution, Karnataka is one of the distribution. So if you see, everything are different, even though the data is same, okay, but the the data distribution is very different. It, you know, hope you understand what I mean to say. Okay, so if you consider everything as a training data, then that's, you consider every distribution as the same means means if you consider everything as a training data, okay, so it produce a model, okay, in such a way that, okay, it means for a single distributions. For example, assume that, okay, so in India we have 30 states, right? But you collected samples from 10 states. Okay, for that you created a model. Okay, so if I try to predict a state which I'm not trained for, okay, will it work? Obviously it will work, but the problem is it won't give 95% accuracy because I trained for 10 distribution, okay, but I tried with 11th distribution. Okay, but how we can generalize it? Okay, generalizing the things in the sense like, okay, I trained for 10 distribution, even though I give the 11th distribution, it should work. Okay, that is basically generalized, right? So what I'll do now, I'll train with this distribution. Okay, so I'll evaluate by using this. Okay, so when I evaluate this, I evaluate for another, I'll evaluate with another distribution, not a training distribution. Okay, the training distribution is different. I train with one distribution, I test with another distribution. So in the test data, I'll get obviously less error. Okay, instead of 95%, I'll get 90% or 85%. Now, I will try to increase this. Okay, so now I wouldn't worry about 95%, I would worry about 85%. Okay, if I don't have test data, then I'll get 95%. Okay, because my W and B are calculated based on this 95%. Okay, I would always think that, okay, I got 95%, I'm okay with that. But when I go to real time, I'll get very different results. So since, I want to generalize it well, so what I'll do, I'll calculate test accuracy. Okay, so this data, I didn't use this for training. Okay, I calculate this for test accuracy. Then I'll try to increase this accuracy. Okay, so when I say the error, you have training error as well as test error. Okay, some people, what they used to do, they'll have 3 split instead of not some people, most of the people. Okay, mostly what we used to do, we have 3 sets of split. Okay, so we have training error, validation error, and then test error. Okay, so what we do, we train, okay, and then we calculate the validation accuracy, okay, and then we test it. Okay, this will give more generalization. So that's the idea. That's why we are splitting into training, testing, and validation data sets. Okay, okay, so now, okay, you got it. Now let's go to the example now. Okay, this is my X, this is my Y. Otherwise, no, I'm sorry. This is my loss, or let's simplicity. Let's take this as accuracy because why? Okay, so I need to choose W. Okay, that should increase my accuracy. Okay, so this is what I need to do. Okay, so I have to increase my accuracy. That's the basic idea. Okay, so in the x-axis, I'll take not W. I'll take we'll take epochs or the iteration. Okay. Okay, I mean to say the iteration. First we'll initialize the value. That's the first iteration. Then we'll little increase the W1 and W2, and then B1 and B1. Okay, that's basically iteration. So in the x-axis I have iteration, in the y-axis I have accuracy. Okay, so now for training data, I'll try to calculate the accuracy. Okay, so first of all, first iteration, it starts with 0, It will keep on increase. It will keep on increase. It will keep on increase. And once it gets some accuracy, then it will be flat. Okay. So this is my training error. Or you can say training accuracy. Okay. During training, this is the accuracy we get, 95%. So simple. We have iteration in the x-axis, accuracy in the y-axis. For the first iteration, I'll get 0 accuracy. Then when I increase the iteration, okay, my accuracy will increase and it reaches 95% at the end. Okay, I'll do the same thing for test data set as well, means validation data sets. Okay, my validation data set reaches some 85% accuracy. Okay, so what I can say, it fitted well for my training data, but it is not fitted for my validation data. Okay, this is called overfitting. Okay, we call this problem as overfitting. Okay, so this is called overfit. So our variance problem. Okay, so now okay, this is overfit problem. Anyway, we'll discuss in the later section in such a way that how we can how we can avoid this overfit problem. Okay, that we'll discuss later. But right now, just try to understand what is overfitting, what is variance problems. Okay, and then now assume that okay, I get a training accuracy of 80%. Okay, and a validation accuracy of 80% again. Okay, so here you can see that the training error itself is very low. Okay, that is called underfitting problem. Underfitting or bias problem. So, okay, so first of all, I'll calculate training and validation accuracy. Okay, so when the training accuracy is good, but my validation accuracy is less when compared to training accuracy, then it is called overfitting or variance problem. When the training accuracy itself is not good, then it is called underfitting problem or a bias problem. Okay, so we have to regularize in such a way that both underfitting and overfitting would be in control. Okay, so this is little I think it's easy concept, not a big thing for you. You can easily understand this if you understand this thing. Okay, so we'll discuss in later part. Okay, that's all about linear regression. Okay, so you understand that we simply starts with one function. Okay, to increase this function we derive loss. Okay, and then we do we evaluate it, we calculate accuracy and loss, and then we'll see overfitting, underfitting, and then we'll choose some parameters to reduce overfitting and reduce underfitting. Okay, in terms it would be a very good fit. Okay, it would generalize well. So that's our whole idea. Okay, now let's go into next topic, which is logistic regression. Okay, so what is logistic regression? So logistic regression is same like linear regression in every terms, but it is for discrete problem. Means the target is you can basically guess the ranges of target. Means what I mean to say, in linear regression the targets ranges from minus infinity to plus infinity, but in case of logistic regression the target ranges from values like 0 to 1, okay, 0 to 10. Okay, so if it is ranges from some particular value, if you know the value about it, for example, think about the employee satisfaction problem. Okay, so you have some data. Okay, using that data you have to predict whether that employee is satisfied or not. So here you have only two cases. Okay, so whether it is 0 or 1. Okay, 0 means employee not satisfied, 1 means employee satisfied. Okay, so now we have to predict male, female, and transgender. Okay, so now you have three things. Okay, so either you have to predict male, which is 0, or female 1, or transgender, which is 2. So here you have 3 class. Here you have 2 class. Okay, this is basically comes in a range, right? Unlike continuous problem, because here the value could be anything. Okay, so minus infinity to plus infinity, but here the value ranges from some particular value, 0 to 1, 0 to 2, something like that. Okay, so we call this as classification problem. Okay, so if it is a If it is a regression problem, we will use linear regression. If it is a classification problem, then we'll use logistic regression. Okay, so within that, we'll have two kind of classification. Here we have only two outputs, 0 or 1. That is we call as binary classification. Okay, so here we have 0, 1 or 2, means it has a value which is more than 2. We call that as multi-class classification. Simple. Okay, so logistic regression would hold for both binary as well as multi-class classification. Okay, simple, means the motivation, the idea why we need logistic regression. Simple, because if the output is not continuous, it is discrete. Okay, then we can use logistic regression. Simple. So, if you see the formula for logistic regression, okay, basically we'll take the same formula. Okay, the hypothesis function is ditto same. Okay, so I'll open other sheets. Okay, so if you see the hypothesis function for logistic regression, okay, let's say y hat, okay, it's same, w transpose b. Okay, w transpose x of b. Okay, so but think about y hat value. Okay, you have input like this 2 and 3. Okay, and w value is 1, b value is also 1. So just substitute this. W into the 2 is 1. I'm sorry, 1 into, means assume that w value is 1 and b value is 1. Okay, so substitute this. 1 into 2, 2, plus 3 into 1, 3, plus 1, it gives 6. Okay, so the target of 6, y hat of 6. But if you see the actual y value, it is 0. Okay, y hat is 6. But if you see the y value, it is basically 0. So now if you take the last, okay, a 6 minus 0, 6. Okay, so think about it. This is again, ridiculous, right? Because my target is 0 or 1, then obviously my y hat would also be 0 or 1. Okay, it shouldn't be 6 like linear regression. So we have to come up with some method in such a way that it calculates y hat within the ranges from 0 to 1. Okay, we need a function like that. Okay, so there are a lot many functions, okay, who can give a value ranges from 0 to 1. Okay, so we'll take one of the function, which is sigmoid. Okay, if you see the property of sigmoid, okay, so it gives value ranges from 0 to 1. So simple, what it will do, if you see the sigmoid function graph, you can understand that. Okay, this is basically the sigmoid function. Okay, so if you see the x-axis, it should be like this. Okay, so this is 0.5. Okay, so you can see that anything below 0.5 is 0. Okay, so this is the 0 value. This is the 1 value. Okay, so anything below 0.5 is 0, and anything greater than 0.5 is 1. Okay, that's basically sigmoid function. If you see the sigmoid function formula, it's basically like this: 1 divided by 1 plus e to the power of minus x. Simple. Okay, this is the sigmoid formula. So maybe you can use this formula. So e to the power, assume that you get some value of x. Okay, and your value of x is some minus value. Okay, so e to the power of okay, so let's assume that you get some minus 1. Okay, so you can use calculator, see what e to the power of minus 1. Okay, it is basically 0.36. Okay, you substitute here 1 plus 0.36. Okay, so 1 plus, I'll just calculator, 1 plus 0.36 is equal to this value. So 1 divided by answer is equal to 0.7. Okay, so now my threshold is basically 0.7, so it will give the value of 1. Okay, and assume that my value is going a much negative. Okay, means I'll get. Okay, let's come to the question. Can you please highlight how do we apply binary classification, multi-classification in financial banking scenario? Okay, see, think about it, this thing, credit card fraud analysis. Okay, so it would be two cases here. Okay, so either the credit card is fraudulent, or the credit card is non-fraudulent. Okay, so here only we have two classes. So that's nothing but, uh, you know, uh, binary classification problem, because either be a fraudulent credit card or a non-fraudulent case. Okay, this is basically binary classification problem. Okay, multi-case classification problem means, think about the same case. Okay, so maybe instead of credit card, like you can think about another scenario which has the target value which is more than 2. Okay, for example, think about the credit card. Okay, so we have to analyze the credit card score, and we have to give whether it is a low score, medium score, or a high score. So here we have 3 targets, right? That is basically multi-class classification problem. Okay, so first you'll see the target and then see the target range. Okay, when the target is binary, we can say that then it is a classification, and particularly binary classification problem. If the target is more than 2, okay, but it is in a range, okay, then it's a multi-class classification problem. Let's take the credit the credit score scenario. And then the second question is, how do I calculate overfit and underfit scenario based on customer who purchased coffee at dinner time interval? Okay, so take the same case. You come up with some data, okay, and then you split the data. Okay, so for example, you come up with some 1,000 number of data, and then you split the data into 800 is to 200. So 800 goes to training, and the 200 goes to testing. Okay, so now you train a model for 800 data, and then you test it with testing data. Otherwise, think like that. Why we need to confuse a lot? Okay, so you collected 1,000 training data. Okay, and then you train by using 1,000 training data. You get some accuracy. Okay, and then you take the model and then placed into cafeteria, okay, and see the real-time scenario. Okay, so you do the prediction on a real-time scenario. For example, you do a real-time prediction for 100 people. Okay, you're testing basically with the real-time data. Okay, in the coffee shop itself. Okay, so now your training error achieves 98%. Okay, and you believe that I will get 98% every time, but in the real time it gives only 80%. That's nothing but overfitting. Okay, so means our model doesn't capture the real-time scenario. Our model doesn't generalize the real-time scenario. It is for particular distribution it calculates well, but it is not doing the same thing for other distribution. Okay, that is overfitting. So underfitting in the sense, during the training time itself I didn't get 90%. I get only 80%. So during the training time itself I didn't get some good accuracy. Then how I can trust the model? I cannot take this into testing at all. I cannot give the real-time input at all. Okay, because during testing itself means during training itself I didn't get good accuracy. That's an underfitting problem. Okay, I hope I understand the question. I answer your question. And then Mahalakshmi asked how we can apply this to categorical classification. I think in the first class, in the statistics class, we discussed about difference between numerical and categorical, right? So, but our linear regression, logistic regression accept only numeric variables. Okay, see, it doesn't able to perform a categorical variable. So then you have to convert this. Okay, so after overfitting and underfitting, we'll discuss this. So let me finish overfitting and underfitting, then we'll discuss about this. Okay, so you understand overfitting and underfitting. Okay, so then we'll talk about the categorical and numerical. Then comes to logistic regression again. Okay, so assume that you have a categorical value like male and female. Okay, you know that we cannot give this value to the model because model works only for numeric thing, because it's all mathematics, right? How it can able to perform a categorical value, a character value. Okay, so what I can do, so I know the value is either male or female. So what I can do, I can put either 0 or 1. Okay, this is one method. We call this as label encoding. Okay, or what we'll do, we'll write M and F like this. Okay, it has two possible values, right? So, either M or F. Oh, okay. So what I do, maybe I'll come to Excel. Okay, let's assume that I get gender, okay, which is either M or F. Okay, so what I'll do, I'll create a value for M or F. So what I'll do, like, okay, the total number of values is 2, so I'll create two values, 1 and 2. Okay, so if male come in, okay, I'll say this is gender male, this is gender female. Okay, if there's a male, then I'll put 1 here and put 0 here. Okay, if it is a female, I'll add 1 here and 0 here. Simple. So this is we call one hot encoding. Okay, so instead of male, I put 1 and 0. So I'll convert this one feature into two feature. Okay, gender M and gender F. And if it is female, I'll move this 0 and 1. Okay, you may ask a question, if I have some 10,000 value, then do I need to create 10,000 variables? Yes, you need to. Okay, so if you don't want to do this, then you can go for label encoding. Label encoding is, if it is male, it is 0. If it is female, it is 1. If it is transgender, it is 2. It's a direct encoding. Okay, so but we'll discuss about the advantages and disadvantages of label encoding in one hot encoding later section. Okay, so right now we'll try to understand the basic concepts. Then we'll see everything. So now let's come to the logistic regression part. Okay, so the logistic regression is if the x value is negative. Okay, if the x value is negative, then we'll get 0. Okay, if the x value is positive, then we'll get 1. Okay, if the x value is 0, okay, then we'll get 0.5. Think about this, x value is 0. Okay, then e to the power of 0 is 0. Okay, I'm sorry, 1. So 1 divided by 2 is equal to 0.5. Okay, we'll get this value. When we get the negative value, we'll get, basically a 0. When we get the positive value, we'll get the 1. Okay, this is what we need to do. So what it will do, you have a hypothesis function. Okay, you have a hypothesis function that will calculate y hat. Okay, so now you need to use the sigmoid function, sigmoid of y hat. Okay, you need to pass y hat to sigmoid. Okay, so the y hat is nothing but x here. Okay, so 1 divided by 1 plus e to the power of minus y hat. Okay, so and then if the y hat value is high, it will give 1. If the y hat value is less, it gives 0. Or sometimes it gives 0.5, 0.2, 0.8, something like that. Okay, simple. So what we do, we convert the values into either 0 or 1, simple case. Okay, so now the actual target is 1 or 0. Our y hat is also 1 or 0. So now it makes sense. We can go ahead to calculate loss functions. Okay, so we understand the problem. This is the classification problem. Okay, so we understand that the target is either 0 or 1 or something like that. Okay, so then obviously if it is a binary classification problem, if the target is 1 or 0, then we'll use sigmoid and convert the hypothesis function into a sigmoid function. Okay, which ranges values from 0 to 1, simple. Okay, so it has so many characteristics as well. This is one of the main reasons we use sigmoid function, but more than that, we do have some characteristics. Okay, because this is basically a non-linear function, so it can fit well as well. We'll discuss about it right now. Don't confuse with linearity, non-linearity, but this has some nice function as well. Okay, so like that, if you think about any function who gives the values ranges from 0 to 1, then you can use that. Okay, let's move on to examples. We have to discuss about one more thing, which is gradient descent. Okay, so before go to the example, I'll discuss gradient descent. Okay, gradient descent is not a big topic. Okay, so don't panic. It's very simple. Okay, see now, take a curve. Okay, so you have W and B value. Okay, and then you have loss as well. Okay, so when you increase the W, okay, what loss will do? It will decrease. It will start decreasing, and then one point of time it saturates. Okay, that's basically this is the parameter or coefficients of weights W. Okay, this is the loss. At the starting point, when the W is 0 or when the W is less, okay, so the loss is higher. When you keep on, increase the W, okay, the loss becomes low and it achieves saturation point. Okay, so you see that, okay, losses keep on decreasing. Okay, so if someone tell us, okay, means someone tell us how I can decrease the W value, okay, based on loss, okay, in such a way that I'll get very loss, means very low loss. Okay, don't confuse. Okay, I'll come again here. Okay, so how we calculate W? Okay, we initialize W value to 0. Okay, and then we'll increment it, by some intuition. Okay, so we'll increment W value and B value by 1. Okay, this is not a good methodology, right? This is how we do. So what we do, first we'll initialize W value is equal to 0 and B value is equal to 0. Okay, then we'll calculate loss. Okay, we understand loss is high. Then we'll increment W is equal to W plus 1, means the previous W plus 1. Okay, then we'll calculate loss again. Okay, so then we'll calculate W again. So, this process is incremental process. This doesn't have any logic. Okay, because every time I cannot increment by 1, right? Sometimes I need to decrease it. Sometimes I need to, increase by 0 0.2, 0 0.5, 10, something like that. So someone has to tell me, how I can increment W and how I can, increment P value. Okay, that's basically gradient descent. Okay, shortly we call this GD. So what gradient descent will do? Okay, so assume that you have some W value, you initialize some W value, and you get a loss here. Okay, so we'll try to calculate the slope here. Okay, so the slope of this particular point is this. So we'll try to calculate the slope. The slope is means the distance between this and this. Okay, now we get the slope, right? Assume that this is 0.2. So we call this as gradient. Okay, so we'll try to calculate the gradient, which is nothing but this value divided by this value. Okay, so means you have some straight line. Okay, let's assume that in a big picture. So when I want to calculate the distance between this, then what I'll do, I'll take the vertical value, take the horizontal value. Okay, this is delta of y, this is delta of x. Then I'll divide this. Means this ranges from, it's not ranges from, this value is basically delta y divided by delta x. Simple. So that's what I'll do here. Okay, so what I'll do, I'll initialize with some W value. Okay, then I'll get some loss. Okay, for that loss, I'll take the gradient, assume that the gradient is 0.2. Okay, so then what I'll do, I'll decrement my W by this value, W minus my gradient. Okay, which is 0.2. So what I'll do, so what W will do, so W will try to increase by some value. Okay, which is 0 minus 0.2, which is minus 0.2. Okay, so now my point came here. So my loss is here. Okay, so I'll use some other color. Now my loss is here. Okay, so for this area, I'll try to calculate the gradient. Okay, for this area, I'll try to calculate a gradient. I'll get some gradient. Then I'll decrease with the W value. From this point, I'll calculate gradient. From this point, I'll calculate the gradient. From this point, I'll calculate the gradient, and then I'll decrease the W value accordingly. So I think that how I coming down. Okay, When it is exactly vertical, means exactly horizontal, then I cannot calculate gradient because the gradient is 0. So when the gradient is 0, then W wouldn't change. So it would be stable then. Then it would be stable and then loss wouldn't decrease at all. Okay. This is basically gradient descent. So what gradient descent will do, okay, so, for loss function, okay, it calculates the gradient value. Okay, we take the gradient value and subtract with the W value. We'll go one step. Okay, that is our first iteration. Then from that point, okay, we'll calculate the gradient. Okay, and then we'll get new W value, that second iteration. Like that, we do many iterations. Okay, at some point, okay, the loss becomes saturated. Okay, it won't increase or decrease. Then we'll fix that point. We'll say that is a final loss and final accuracy. Simple. Okay, that's the gradient descent. So if you revisit, okay, so first we'll calculate hypothesis function. Okay, from that we'll take loss. Okay, and then we'll try to decrease the loss by using gradient descent method. Simple. Okay, in case of logistic regression, we'll do the same thing. Okay, but with one additional step. Okay, so we calculate we calculate hypothesis function. Okay, we convert the hypothesis function into sigmoid function, which means the value ranges from 0 to 1. Okay, then we'll use loss function, then we'll use gradient descent. Okay, simple. Okay, so before that, we have to do one more thing, which is, what about the loss function in case of logistic regression? Okay, in case of linear regression, you know that. What's the loss function? Y minus y hat whole square, simple. Okay, so in case of logistic regression, can we use the same function? Because, think about it. Okay, because the sigmoid gives either 0.2, 0.8, anything, which is ranges from 0 to 1. Okay, so if you use the same linear regression formula, it will be very different because 1 minus 0.2 is 0.8, but we don't need like this. We need something like this, 1 minus 0 or 1 minus 1. Okay, so, someone has to, so obviously, if we use this, means if we use loss function for linear regression, then obviously, we do have a chance to, that is not generalized well, that is not suitable for sigmoid function. Okay, so we need to come up with a new loss function for sigmoid function. Okay, otherwise you think about it. Okay, so we already discussed this. Okay, so we, in the starting class, in the first class, we discussed about Bernoulli distribution, right? So we discussed about so many distribution, Bernoulli distribution, normal distributions, and then exponential distribution, beta distribution, gamma distributions. We have discussed about so many distributions, right? Okay, and that distributions basically tells, in a Bernoulli distribution, takes the value ranges from 0 to 1. Okay, normal distributions take the value ranges from minus infinity to plus infinity. Okay, so think that concept. Okay, so now, okay, so our problem is binary classification problem, which takes the value ranges from 0 to 1. Okay, to which distribution it is fitted in. Okay, as basically binary distribution. Okay, what is the probability density function for binary distribution? The probability of x into 1 minus probability to the power of 1 minus x. Okay, this is basically our Bernoulli distribution, right? So p to the power of x into 1 minus p to the power of 1 minus x. Okay, but when we define any formula, okay, what we used to do, okay, we used to sum it up rather than product. Okay, we prefer sum rather than product. But if you see this formula, this is basically product, not a sum. Okay, so we'll try to convert this into a sum. What we can do, we can apply log function on top of it. Log of this formula. Okay, if you apply log function, what it do, it's split like this: log of p to the power of x plus log of 1 minus p to the power of 1 minus x. Okay, so let's use the power rule here. Okay, so if you know the power rule of logarithm, okay, it brings this x front. So x log of p plus 1 minus x log of 1 minus 2. Okay, this x is nothing but, in our case, the actual value y. Okay, this p is nothing but y hat plus 1 minus y log of 1 minus y hat. Simple. So this is the last function for logistic regression. We didn't do anything. Okay, so we understand the target range, it is 0 to 1. Okay, then in the statistics class we discuss about so many distributions, and one of the distribution is Bernoulli distribution that also takes a value range from 0 to 1. Okay, so we use the probability density function of Bernoulli distribution. Okay, then we just want to convert this product into a sum. Okay, so we apply log function. Okay, we get something like this. Then we use the power rule. Okay, we derive the equation like this. Okay, so now y into log of y hat plus 1 minus y into log of 1 minus y hat. That's our formula. Okay, so now think about it. Your y value is 0, your target value is 0. Okay, and then you get some y hat value which is 0.2. So log of 0.2 will always convert a value into close to 0 or close to 1. Okay, so that's why we use log function. Okay, plus there are so many constraints. Actually, we have so many explanation why we derive this kind of equations. Okay, this is not a one point, basically it has multiple point, but here we'll discuss about the major point. Okay, just to first we try to understand this. When you understand and when you're able to apply these concepts, then we can think about all those things. I means all those evaluations, all those parameters, all those reasons. Okay, right now, I don't want to go into depth because obviously that will lead into a confusion. Okay, so right now try to understand the logistic regression. Okay, so now the same thing in terms of logistic regression, we have hypothesis function. Okay, in terms of linear regression. Okay, in terms of logistic regression, in terms of linear regression, we have hypothesis function which is y hat is equal to W transpose of X plus B. Okay, logistic regression also we'll have same formula. Okay, but we'll add one more formula which is sigmoid of y hat. This is hypothesis function, and then we have loss function which is here y minus y hat whole square. Here this function. Okay, and then we have gradient descent. Okay, so gradient descent is same. Gradient descent is, it will try to find the slope. Okay, and then it will decrease by the slope step by step. Simple. Okay, that's all about logistic regressions. So I think now you are very clear about how linear regression and logistic regressions work. Okay, because this formula is very important. Okay, no need to remember the formula, but understand the flow. What is the first, what is the second, what is the third, what gradient descent will do. This kind of understanding is more than enough. If you understand this, then you can understand any kind of algorithms, because if you see any family, any mathematical algorithm family, it will follow this flow basically. Even if we go to the neural networks, deep learning, it will follow the same flow. Okay, with some differences. Like, we have seen some differences between linear regression and logistic regression, right? Even if the flow is same, those kind of differences you'll find in each and every algorithm. There is a difference between logistic regression and support vector machine. There is a minor difference between support vector machines and neural networks. So like that, the flow is same, but you'll have some additional things in each and every algorithm. Okay, so now let's go to some examples. Okay, so now we'll try to apply logistic regression by using scikit-learn as well as stats model API. Okay, so first we'll try with stats model. Okay, so we'll have an input like this. Okay, so we'll have an input like this. The input is, okay, the input is this. Okay, we have to predict admit. Okay, admit is either 0 or 1. Okay, it's basically college admission. Okay, so we have some inputs like GRE score, GPA score, and rank. Okay, so based on this, we'll try to predict whether he can admit to the college or rejected. Okay, if it is 0, it is rejected. If it is 1, it is admit. Okay, so this is the input. So obviously we know that the target ranges from 0 to 1. This is obviously a binary classification problem. Okay, sometimes you may find that yes and no, yes or no. If it is admit, it would be yes. If it is not admitted, it should be no. Okay, so in that case, we'll change it to 0 to 1. Okay, we'll use label encoding. When it is yes, we'll use 0. We'll replace no with 1. Simple. Okay, so means it will take two possible values, either 0 or 1. Simple. So we call this a binary classification problem. So we'll use logistic regression. Okay, so now I'm just rename rank into prestige, because rank is a method in pandas. So it is good to use some proper variable names. Okay, so now admit, GRE, GPA, and prestige. Okay, now we'll say summary statistics. Let's not worry about it. Okay, let's not worry about all this. Okay, now we need to create dummy variables. Means we need to convert the categorical variables into numeric variables. Okay, in the example, which is categorical variable? Okay, I think GRE is numeric, admit is numeric, GPA is numeric, rank is, it looks like numeric, but see, this is either 3, 1, or 4, or 2. Okay, so obviously this is not a numerical, because numerical in the sense, numerical value basically not only numbers, but it also ranges from minus infinity to plus infinity. Okay, categorical in the sense, even if it is a character, even if it is a number, it is basically discrete. Okay, so this is basically discrete. So I need to convert this into a categorical. Okay, so there are two possible things, right? One is one-hot encoding, another is label encoding. So this is already aligned with label encoding. So I can leave this and I can go to the calculation. Okay, so this is label encoding basically. This is already a label encoded. But do I need to seriously convert into one-hot encoding? Because yes, because one-hot encoding is better than the label encoding. Okay, because gradient descent suffers with label encoding. Okay, logistic means the last function suffers with this label encoding. Okay, so if you use one-hot encoding, then the last function would be more accurate. Gradient descent also would be easy to step down. Okay, so but if you ask me how, we'll discuss that. Okay, in later part. But right now, if I discuss, you may have a chance to confuse with that. So let's not worry about it. Okay, so but let's assume that, trust me, okay, if you use label encoding, there will be a problem with a gradient descent and last function. But one-hot encoding, you don't have any such problem. Okay, so now we know that one-hot encoding is always best. Okay, so whenever you see a discrete variable in your input, okay, try to convert into one-hot encoding. Okay, now how we can convert a variable into one-hot encoding? Okay, in pandas, there are one method that is available, a get dummies. Okay, so pd.get dummies. Okay, this will convert any categorical variable into one-hot encoding. Okay, so here we need to convert prestige. Okay, so now I'll execute this. So I didn't do anything. Okay, so I call pd.get dummies of my data from of prestige. Okay, and then I use prefix of prestige, means it basically create 4 variables here, 3 to 4 variables. Okay, so 1 for 3, 1 for 4, 1 for 1, 1 for 2. Okay, so keep the label with suffix, which prefixed with prestige. That's what I said. Okay, you can see that prestige of 1. So basically, prestige takes 4 possible values: 1, 2, 3, 4. Okay, so so I said prestige of 1, prestige of 2, prestige of 3, and prestige of 4. Okay, so here the prestige is 3. Okay, so it puts 1 in the prestige 3 and puts 0 everywhere. Okay, so here the prestige is 1, so it puts it writes 1 in the prestige one and it writes 0 everywhere else. Okay, very simple. Okay, so in pandas, within a single line, we can achieve one hot encoding. Okay, now we one hot encoded it. Okay, now this is my final input. Okay, you can see that I converted everything. So we call this as a data preparation stage, our future extraction stage, our future preparation stage. Okay, for simplicity, let us call us data preparation. So we're done with the data preparation. Okay, so we found that this is a binary classification problem. So we know that we're going to use logistic regression. Okay, so everything is numerical value rather than prestige. So we convert the prestige into one hot encoding. Okay, so now what we need to do? Okay, okay, so we need to fit it, we need to train it. Okay, so when you train, obviously you need to give two things. One is your target. Okay, in stats model you have logic function. Okay, so logic function requires two things. One is your target, another is your features. So the data of training columns like GRE, GPA, prestige, everything comes under this, and admit is the target. Okay, then I call fit function. Okay, this will fit. Okay, this will run hypothesis function, loss function, and gradient descent. Okay, and it will fit and it send me the current accuracy. Okay, it said, okay, the current function value, the current accuracy is 0.5%, 0.57 means 57%. It has 6 iteration. Okay, so let's go to another example. So you understand this, right? What happens here? Simple. It runs gradient descent, loss function, hypothesis function, and then it calculates the accuracy for training data. Simple. Okay, so when you summarize the result, okay, then you can see all this. Okay, what is the R square value? Okay, what is the log likelihood? Okay, let's not worry about log likelihood. Okay, so let's worry about coefficients. What is the coefficient? Okay, for GRE, what is the coefficient? For GPA, what is the coefficient? What is the coefficient for prestige 2, prestige 3, prestige 4? And what is the intercept? The B value, bias value. Okay, what's the confidence interval range? Okay, what is the P value? Okay, all the P value is less than 0.05. So we need not worry about it. You got it right. So you try to, you mostly identify fields, P value, 95% confidence interval, R square value, okay, coefficients. Okay, so this is enough. So through that, we can tell that, how model is good or bad. Okay, so now we'll try with scikit-learn. That's very important. Anyway, in practical application, we'll use scikit-learn. Okay, we'll try logistic regression with scikit-learn. Okay, so here we take different data sets. Okay, the data set is a fair data set. Okay, it's basically like it was derived from a survey of women in 1974 by Red Book magazine, which basically, they take a observation, they take a samples from married women. Okay, whether do you have any affair or not, whether the married woman has any affair rather than husband. Simple. Okay, that's a survey. Okay, that survey will take some input variables. Okay, rate marriage. Okay, what about a women's rating of her marriage? Okay, whether it is going poor or good, something like that. And what is the women's age? Number of years married, number of children. Does she have any religious ideology? Okay, what about education, occupation? Okay, and then what about the occupation of husband? And then the target is affairs. Okay, what is the time spent in extramarital affairs? Okay, so it's funny, but that's the data. Okay, that's the data available in Red Book magazine. This is the real survey. Okay, so now this data set contains 6366 observation, means 66,366 samples. Okay, and 9 features, 9 variables, including target. So 8 features and 1 target. So now we see the affair. Okay, and then we'll see the values of affair, and then from that we'll see whether we can use linear regression, logistic regression. Let's go with that. Okay, so I import all the required things. Obviously, I'll import NumPy, Pandas, Matplotlib, and scikit-learn. Okay, so if you see the data set, Okay, if you see the affairs, it is either 0 or 1, whether she's affair with someone or whether not. Okay, simple. So obviously from the target, we understand that this is a logistic, this is a classification, binary classification problem, and we use logistic regression. Okay, so basically if you see this thing, okay, so we get logistic regression of class, and then we use train test split from scikit-learn. Okay, so know that, okay, we convert the value, the observation, the samples into train and test data sets. Okay, and then metrics, which will tell the accuracy and everything, and then the class validation score. Okay, so class validation score, which is nothing but the test score. Okay, so we have train data set, test data sets. Okay, we'll calculate the hypothesis function by using training data sets. Okay, and then we'll get the score for test data sets. We'll consider that as accuracy for much better generalization. So we already discussed about that. Okay, simple. Now we got the data sets. Okay, so let's not worry about it. These are all some, data exploration, how data is aligned. Okay, let's not worry about it. Okay, now let's come to the real part. Okay, so before apply logistic regression, you have to convert everything. Convert in the sense means you have to convert a categorical value into numerical value using one-hot encoding. That is what we do here. Okay, so we used here we use some other thing called D matrices instead of dummy variable, get dummy, but you can use dummy as well. Okay, so anything is possible. So scikit-learn provides D matrices. Okay, so I'm sorry, this is from PATSI model. PATSI model provides D matrices. Here also you can calculate, you can convert categorical into numerical. Okay, so that is what we did here. Okay, now you have the data available. Okay, in the X, you have the features. In the Y, you have the target. Simple. Okay, so we took the input. Okay, so we understand the problem, and then we find how many values are categorical. We convert into numerical. Okay, now we come up with training data sets. So training data set consists of X and Y. Simple. So we come up with training data sets. So the training data sets consist of features and target. Okay, so X and Y. Okay, so we got it now. So now we can apply logistic regression. Okay, so what we can do, so we can define the model logistic regression, and then we can fit by using X and Y. Okay, then we calculate the score, model.score, which is the accuracy score for training data sets. The accuracy score is 72.5%. Okay, yeah, it's a decent accuracy. It's not a bad accuracy. 73% is a decent accuracy. Okay, so then if you want to calculate like what is the average percentage that the women have, the married women has affairs in US. Okay, it's almost 32%. Okay, so now what we'll try to do, we'll try to understand the coefficients. Okay, so model.coefficients will give all the coefficients. Okay, so now you can see that the intercept has this coefficient. Okay, so we have multiple variables. Everything has a coefficient ranges from 0 to 1. So if it is closer to 1, so you can see the relationship. Which particular field, okay, has a more relationship with the affairs. Okay, you can see that the occupation. Okay, if she's working in a good job, she's completely independent and she doesn't worry about the laws, right? Okay, so she doesn't dependent on husband. So obviously she does have a more chance with the affair. Okay, clearly tells that. Okay, and then here also you can see that this is also occupation, means we do have 6 occupation, right? Occupation 2, occupation 3, occupation 4, occupation 5 and 6, means we have 5 variables. Okay, this is clearly tell us some occupations. Okay, so mean the occupation 3 and 4, kind of they have affair. Okay, they may be in some occupation. Okay, that's more prone to affair. Okay, so we can generalize this. So if they are walking, obviously they do have more chance to be an affair. Okay, because you can understand logically, yes, that's possible. Because if you are in home, obviously you do have a chance. You don't have a chance to see most of the people. But if you go outside, you you have more chance to see people's, and then if you find a good match, obviously you'll do that. Okay, then what is the occupation of the husband? It doesn't. Okay, but if you see this, okay, it is negative correlation. Okay, so whenever this okay, so it might be something rape marriage, I guess. Okay, so as well as see some of the things is, okay, so the point is, from the coefficients you can understand what is the relationship between features and target. Okay, so if it is closer to 1, that, okay, whether it is +1 or -1, okay, if it is closer to 1, then it has a relationship, a good relationship between features and target. If it is closer to 0, then it doesn't have much relationship. If you see this value particularly, okay, children, it does not at all matter. Okay, so it means it doesn't have any relationship at all. Okay, you cannot say that if they have children they have affair. Okay, so it is from this you cannot say anything. Okay, so like that, this is also correlation. Okay, years of marriage doesn't matter. It does matter, but it is not a matter. Age is also not a matter. See, age is not all a matter. -0.05. Okay, so that's important. Okay, so from the coefficients you can tell what kind of relationship it does. Okay, then we can go ahead with evaluation. So we created a test set. Okay, so using train test split, okay, I'll calculate training data set. So what I'll do, I have X and Y. Okay, I'll convert 30% split. Means I'll for test data I'll give 30%. For training data I'll give 70%. Okay, so now I have X train, X test, Y train, and Y test. Okay, in the training data, X train data, I have 70% of training data. In the Y test, in the X test and Y test, I have 30% of data. Simple. So what I do, I'll basically fit by using X train and Y train. I'll calculate accuracy. Okay, so here my accuracy is some range. Then what I'll do, so you can, if you want the accuracy, you can use this model 2 dot score of X train comma Y train. Okay, same accuracy, 73% accuracy, even though we split the data. Okay, then what I'll do, I'll try to find the accuracy for X test. Okay, so what I'll do, I'll give only X text, and then I'll try to predict the output. Okay, I predicted output. Then what I'll do, I take this probability and compare with the original output, Y test. Okay, so I don't think this is difficult to understand. Okay, so we have X train, Y train. Okay, we fit a model. Now we have X test as well as Y test. Okay, so we already created a model by using training data sets. Okay, so now what I'll do, I'll take only X and give it to the model and calculate Y predict. Okay, now I have Y test and Y predict. Okay, for this I'll calculate the accuracy. Simple. Okay, so now I take only X test and predict output for, I predict output, which is Y predict. Okay, then what I'll do, I'll take Y test and the predicted value and then try to calculate the accuracy score. Okay, which is also 73% accuracy. Okay, let's not worry about ROC AUC score. Okay, we'll discuss about that. But accuracy is, let's worry about accuracy score. The training accuracy is also 73%. The test accuracy is also 73%. Okay, so obviously, yeah, it is not overfitting. It's neither overfitting nor underfitting. It's a good fit. Okay, so we need not do anything. And then we do have something called confusion matrix. We'll discuss about it. So let us discuss about the previous thing. So here, test accuracy, training accuracy is 73%. Test accuracy is 72%. So we don't have any overfitting underfitting problem. Okay, but let us think about again. Okay, so we got training accuracy only 73%. So we can say it is underfitting problem. Okay, so we don't have any overfitting problem, but we have underfitting problem. So what we need to do, we need to increase the training accuracy first of all. Okay, so we can calculate p-value, we can calculate multicollinearity. Okay, we'll try to reduce some features. Okay, and then we'll try to increase the accuracy. When you get some decent accuracy like 90%, then we'll again get the crash validation accuracy. We'll compare that. If everything is good, we can go ahead with that. Okay, so now let's talk about some interesting things. Okay, let's talk about a practical example. Okay, let's take one practical example, a cancer prediction problem. Okay, so we need to means we are going to write an algorithm that will predict cancer. Okay, so you know that the cancer prediction problem is a binary classification because we are going to predict either the particular people has the particular guy has cancer or not having any cancers. Simple. Okay, so our target is either 0 or 1. So this is basically discrete value ranges from 0 to 1. So we know that this is a binary classification problem. So we'll use logistic regression. Okay, so now we got 99% accuracy. Okay, can we believe this model? Very simple question. Okay, I have a cancer prediction problem. I know this is a binary classification. I apply logistic regression and I got 99% of accuracy. Now I'm asking myself that can I believe this model 99%? It's a question because let's take 10 samples. Okay, so I have X, Y. Okay, this is my first sample, second sample, third sample, fourth sample, fifth, sixth, seventh, eighth, ninth, and 10th. So assume that I collected samples from real people. So most of the people doesn't have cancer because cancer is a very rare disease. So obviously my output is no cancer, 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 and only one cancer portion. So out of 10 samples, I have only one sample for cancer, another 9 samples are not having cancer. Okay, now assume that, okay, this is my Y actual value. Okay, now for testing, I'll predict Y predict value. Okay, I predicted 0 to everything. Means you can see that my model predicts everything as 0. Okay, so what accuracy I'll get? This is correct. Okay, out of 10, 9 are correct. Only 1 is wrong. So you'll get 90% accuracy. But how come I didn't predict anything right? I predict everything wrong because see, this is important, right? Because a model predicts only one thing, which is 0. Whatever you give, it will give 0. But even then, since this case is a very rare case, I get 90% of accuracy. But model doesn't do anything. It just predicts 0. Okay, so from that you can understand accuracy is not a matter. Accuracy is matter, but some cases not a matter. So we call this problem as a skewness problem. Means we don't have a partial sample. Means we don't have a good sample. Okay, we do have 2 classes, but since it's a very rare problem, out of assume that we collected some 10 million samples. Okay, so out of that only 50 samples has cancer patient, and other samples are not cancer patient. Okay, so obviously we cannot collect more and more samples, right? Because it's very rare disease. Obviously, we cannot collect 50 and 50 samples. 50% of cancer people, 50% of non-cancer people. We cannot do that. Okay, but at the same time, we need to come up with a model in such a way that predict nicely. Okay, that we'll see later. Okay, we'll come up with a support vector machine in the later section. But before that, okay, let's worry about this problem. Okay, the model doesn't do anything. Okay, doesn't learn at all, but even then gives 90% or 99%. Why? So we need to come up with another scores, okay, that tells exactly the model prediction. Okay, so we need some other scores that would tell the real thing. Okay, that is nothing but confusion matrix. Okay, so what confusion matrix will do? Okay, let's take a case like this. Okay, confusion matrix. Okay, so let's take actual value, predicted value here, actual value here. Okay, we have actual and predicted. So here we have predicted positive and predicted negative. The actual is positive and negative. Okay, simple. So the actual value is 1 or 0, predicted value is 1 or 0. So I predicted positive, okay, but the actual is positive. So think the same case, y actual, y predicted. Okay, we have 10 observations. Okay, so the actual is 0, 0, 0, 0, 1, and here everything is 0. Okay, so now this is actual predicted. How much I predicted positive? I didn't predict positive at all. Everything is I predicted everything is negative. Okay, what is the actual positive? 1. Okay, so I predicted positive 0. So here I didn't predict anything. So predicted positive 0. I predicted everything as negative. So I didn't predict anything positive. Okay, now come to the second case. Okay, I'm sorry. Yeah, how much I predicted 0. Okay, how much actually 1? Okay, out of 10, all 10 I predicted 0. Okay, and actually 1 is, okay, it's simple. You think like this. Okay, I predicted 0. Okay, but actually is also 0. So here I predicted 0, actually is also 0. One example. I predicted 0, actually is also 0. I predicted 0, actually is also 0. Like that, 9 samples, I predicted 0, actually is also 0. So you can see that 9 examples. So predicted 0, I predicted negative, actually is also negative. Okay, but I predicted 0, but the actual is 1. Here only 1 cases. Okay, let's put some color here. Okay, simple. So now, okay, so this case is very simple. Okay, I predicted 0, actually is also 0, just 9 examples. I predicted 0, but the actual is 1, which is only 1 example. Now I predicted 1, but the actual is also 1, but I never predicted 1, so it is 0. Okay, I predicted 1, but the actual is 0. This is also 0. So if you sum this, the total should be 10. Okay, from that you can understand I predicted 0, okay, but the actual is 1. So what it would tell me, okay, so it will give 2 scores. From there I'll calculate 2 scores, recall and precision. Okay, so before that, what is this value? Okay, I predicted positive, but the actual is positive. So this is true positive. Okay, means TP. Means I predicted positive, actually is also positive, so true positive. Here I predicted negative, but the actual is positive. Means I predicted negative, but the actual is positive, means false negative. Okay, here I predicted positive, but the actual is 0, so false positive. Okay, here predicted negative, actually is also negative, just true negative. Simple. So from the confusion matrix, I come up with 4 values: true positive, false negative, false positive, true negative. Okay, so here take this true and true values alone. Okay, so here, okay, I predicted negative value 9 times, but I never predicted true positive. So from the true positive, you can understand, okay, what is my accuracy? Means whether I predicted positive or not. Here, my model never predicted true positive. Okay, so here, so you can say that out of 10, okay, 0 is true positive. So it never predicts. What is false negative? Means I predicted negative, okay, but it's false again. So I predicted negative, okay, but it's actually false. Okay, that is not negative, that is positive. So this case, I predicted negative, okay, but that is false. That is basically actually is 1. So I predicted one thing false. Okay, so based on that, we'll come with recall and precision score. So I'm not going to tell the formula here. Okay, that's the exercise. Just go ahead and try to understand what is the formula for recall and precision. Okay, what recall and precision will do, it's something like 0 to 1. So it also gives accuracy ranges from 0 to 100%. Okay, so I will calculate recall score and precision score with the accuracy score. Okay, if the recall score and accuracy score is less than 100%, say 20%, and this is 30% and this is 40%. That is not a good prediction. This also should post to 1. Okay, so through recall and precision, I can understand, okay, whether my data is sensitive to skewness and not sensitive to skewness. Okay, my model. So here you can see that my model is sensitive to skewness. Okay, so that recall and precision will tell. Simple. Okay, so we can summarize this. Okay, so we can trust the accuracy score, but the point is if you don't have any skewness in the data. Okay, if we have any skewness in the data, then obviously we cannot trust the accuracy score. That point of time we can calculate recall and precision score. I'm sorry, recall and precision score. Okay, through that we can understand how well it behaves for skewness. Okay, if it is really 95% and 95%, then okay. Even though my data has skewness, it fitted well. It close to accuracy score. I never worried about it. Okay, so but when I'll worry when the percentage is very less. Then I'll try to come up with some solution to increase the accuracy. Okay, so that this score is also very important. Okay, we cannot blindly trust accuracy score. Okay, that's what we are calculating here. Okay, so if you see the next thing, we come up with a confusion matrix. Okay, the confusion matrix will tell me all this. Okay, precision, recall, and F1 score is also if you see the F1 score, the formula is 2 into PR divided by P plus R. Means P is precision, R is recall. So F1 score is basically the trade-off between precision and recall. Okay, so now we see this. Okay, my precision and recall is good. Okay, if you see the average F1 score, average recall score, average precision score, it close to the accuracy. So I don't have any skewness in the data. Okay, so from the confusion matrix, you'll understand this. So now, as I said, okay, we'll now we discussed about what is confusion matrix, what is accuracy score, what is recall, what is precision, what is F1 score. Okay, so last time what we did, we split the data into train and test, then we test the accuracy. But as I said, instead what we can do, we can have cross validation as well. Okay, so instead of split into 2, split into 3. Okay, that will generalize the case very well. Okay, that's what we are going to do here. So we are going to evaluate model using cross validation. Okay, so here I'm going to use a scikit-learn class, which is cross validation score. Okay, the logistic regression, and my actual input is X and Y, and I'm using some cross validation of 10. Okay, this is called K-fold cross validation. Let us discuss about it. What is K-fold? Okay, so now assume that you have you have trained data, and this has 500 samples. Okay, so think about it. What I can do basically, I can split this data into 10. Then I'll train 10 times. Okay, I'll have 10 models. Then while predicting, I'll take my X value and hit all the 10 models. Okay, the first model gives 1, second model gives 1, third model gives 0, fourth model gives 1. Like that, all 10 models give some output. Okay, I'll see which, what is the output value I get maximum from the 10 models. Which value I get from the 10 models. So what I mean to say, the target is either 0 or 1. Okay, so whether I get 1 most of the time or 0 most of the time. So you can see that I get 1 most of the time. So the output is 1. Simple. So we call this the ensembling techniques or a K-fold cross validation. So what I do, instead of create a single model, okay, I create 10 models. Okay, and then finally I'm ensembling it. I'll summarize it. I'll average it. Okay, that's the concept. Very simple. Okay, so now I'll take this 5,000 samples. Okay, I'll split this into training as well as cross validation data. Means X train and XCV. Okay, I'll randomly split some 70% data to extrain and 30% data to validation. Okay, this is the first class validation. Okay, assume that understand that this is a random sample. Okay, and then again I'll take the random sample and then I create the second training data. Like that, I create 10 training data. So obviously, this data wouldn't be same. In the first data would not be same to the second data because it's a random sample. Obviously, there will be a randomness in all data. Okay, now I'll train all 10 models. I'll create 10 models. Now, when I predict it, I'll hit all the 10 models and then I'll ensemble it, I'll average it. Then, I'll see whether one is having a high, one is appearing high number of times or zero is appearing high number of times. Accordingly, I'll choose the output. So obviously, this will give more generalization because instead of training one time, I train 10 times. Okay, so obviously it gives more generalization. So if I just run this, you can see that this is the average accuracy. Okay, that's also 73% accuracy. So I can say that generalized well. You can see even if I deploy this model into production, okay, in real time, this will perform better. So before I deploy the model, I have to do all this test. Okay, so this is, we call it as a k-fold class validation. Okay, the value of k is 10 here, so we call as a 10-fold class validation. Like that, I can choose any number of k values. Okay, what is the disadvantage here? The only one disadvantage is the training time. Okay, so to create one model, assume that it takes 1 hour. To create 10 models, it takes 10 hours. Depends on your data. So the running time, the training time is increased by 10%, means increased by 10. Okay, so that's one thing. Okay, so but if your input is very small, then you can go ahead with k-fold class validation. If your input is very big and you don't have that kind of system requirements, then instead of 10-fold, you can use 4-fold, 3-fold, 2-fold, something like that. Okay, so that's all about class validation score. So that's all about linear and logistic regression. So let's summarize this. So today we started with a recap of linear regressions. Okay, so we generalize the algorithms. Any algorithm has hypothesis function, loss function, gradient descent. Okay, but it will change accordingly. If you see the hypothesis function of linear function, which is W transpose of X, but if you see the same hypothesis function for logistic regression, it is sigmoid of W transpose X. Okay, you know why? Because hypothesis function is continuous, means linear regression hypothesis function is continuous, but logistic regression hypothesis function is discrete. Okay, and if you see the logistic means last function of linear regression, it's simply y minus y hat of whole square. Okay, but if you see the last function of logistic regression, okay, which is very different, means y into log of y hat plus 1 minus y into log of 1 minus y hat, and we derived it mathematically. Okay, so we already seen Bernoulli distribution. Okay, that is good for discrete variables. Okay, so we took the Bernoulli distributions and we derived the logistic regression cost function. Okay, and then we discussed about gradient descent. Okay, so we have a curve. Okay, the x-axis is weight, y-axis is loss. Okay, so we'll initialize w and y value. Okay, we'll calculate some loss. For that loss, we'll take gradient. Okay, so gradient has some value. Okay, we'll decrease the w value by the gradient. We'll get new loss, and that new loss would obviously better than the first loss. Okay, so like that, we'll decrease the loss by using gradient descent step by step. And when it saturates, we'll stop that. Okay, that is the final loss. And from the loss, we'll calculate the accuracy. Okay, and then we discussed that yes, we cannot trust the accuracy because if the input has skewness, we cannot trust the accuracy. For that, we can call recall and precision score through confusion matrix. Okay, if the recall, precision, and F1 score is good, then we can trust the model completely. Okay, but even then, how to generalize well. It may fit to my training data, but it may not fit to test data or the real-time data. How I can make sure that in the model itself. Then you can use k-fold class validations. Okay, you can instead of a single training data, you can come up with a 10 training data, and then you can assess the model. If it gives better percentage, then we can completely trust the model. Okay, so we discussed about all things. We discussed how we can use logistic regression scikit-learn. Simple. We have some we need to call a logistic regression class, then train test split, class validation scores, metrics accuracy. Okay, we call this functions. Okay, and then we'll fit it by using trained data, then we'll predict it, then we'll try to calculate the accuracy. Okay, so means it may be a 10 line of code. Okay, so we'll complete everything within the 10 line of code. How simple it is. Okay, so that's what we discussed today. Why we need to convert categorical data. Okay, so let's answer this question. Okay, so the first point is, okay, logistic regression and linear regression is a mathematical formula. So if you see the hypothesis function, okay, this is W transpose of X. So W is some value, let's assume that 0.1, and X is some numerical value. Otherwise, if I give some, instead of numerical value, I pass male, what happens? It would give error. So I have to convert all the character data into numeric data. Okay, so this is one essential, this is one point. But categorical data is not only male and female, it is also 0 and 1. Okay, instead of male, I can pass 0. Then obviously it gives me a nice, it won't give error. Okay, but why? So we call this the label encoding, right? So label encoding is enough. So why I need one hot encoding? So that's the question basically. Okay, so obviously we cannot use male and female. Okay, so instead I convert this into label encoding, which is, for male I move 0, for female if I move 1. If I have transgender, then I'll move 2, simple. And if I have others, okay, I'll move 3. Okay, whatever it is. So this is the label encoding. Okay, so this will solve my mathematical error. But why I need to convert to one hot encoding? Why it is necessary? Because this will come up with 2 values. Okay, means 1 0 and then 0 1. Why I need this basically? Okay, so the one point is, okay, so you need to clearly tell to the algorithm, okay, what is what. Okay, so if not, it has a problem. Okay, think about the male and female case. Okay, so it's a mathematical algorithm. So it might have a chance to take as a numerical value. 1 is higher value, 0 is lower value. Okay, that's a problem. This is one point. Okay, the second point is, okay, you understand, right, what I'm trying to say. So instead, if I use 10 20, I can use, right, 0 to, instead of 0 to 1, I can use 10 and 20. Okay, I can use any kind of label encoding. But if I keep on increasing this value, will my model change? Yes, obviously change. Instead of 0 to 1, if I use 10 to 20, obviously my model will change. Okay, so how I can trust label encoding? Obviously I cannot, because if I have a categorical value which consists of 10 classes, okay, then I'll keep on improve this. So if dividing 0.1 into 5 is different than dividing 0.1 into 0. Okay, so I need something which gives the consistent value between 0 to 1. Okay, so I need to restrict myself with 0 to 1 instead of going like this. Okay, that's why I use one hot encoding. So one hot encoding, I wouldn't extend my range at all. My range is always constant, which is 0 to 1. Whatever the cases, if it is transgender, again it is 0 then. Simple. Okay, so my values would always range from 0 to 1. So mathematically that is good. That is good for loss function, that is good for gradient descent, that is good for hypothesis function. So that's why we convert everything into one hot encoder. This is necessary. Okay, go through linear regression, logistic regression. Okay, so try, maybe you can, as I said, like we have talked about Kaggle, right? So Zillow price competitions. So take that, okay, try to apply all this model using scikit-learn, okay? So then you can understand things better, okay? So next we talk about another algorithms. Okay, thanks everyone then.
A cat killed. Average is dead.